Hello students, in previous lecture we have studied about the physical properties and some periodic trends of transition elements. Today we are going to study about the color of the transition elements. All of you aware of that transition elements are most of the colored or colorful. For example, Au gold, it is yellow in color. Copper, which is red in color. Cu2 plus ion, which is present in copper sulfate, it is also blue in color. That means their compounds or solutions of their compounds and transition elements itself, they are also color. The color of the substance depends upon the portion of visible light absorbed by the elements of a particular wavelength of electromagnetic radiations. Then we will discuss detail about the color, that property of transition element. Then see here, we have to discuss on the reason of the colored compounds of transition elements. Then what are the reasons behind that D block elements, that is transition elements, are colorful and their compounds and complexes are also colorful. All of you aware of that compounds of the transition elements are whether it is ionic or covalently bonded compounds. Then ionic or covalently bonded compounds of transition elements are also colored, and that is depends upon number of unpaired electrons present in the n-1d orbitals. Color of transition elements, it is depends upon number of unpaired electrons present in valence orbital, that is n-1d orbital. For example, if there is one unpaired electron present in scandium, then if one unpaired electron is present in outermost orbital of the element, then it is purple or blue in color. Similarly, if there is 0 unpaired electrons in zinc, 3d orbital is completely filled. That means 3d 10 electronic configuration is there and number of unpaired electron is 0. Therefore, zinc is colorless or it has silver color. That means here the color of compounds of transition elements or color of transition elements depends upon number of unpaired electrons present in n-1d orbital. Then if the element is in atomic form or it is in isolated form, then 5d orbital, all of you aware of that, the d orbital, that is 3d orbital, it is of 5 subshell. There are 5 subshells are there, suborbitals are there. Then electrons present in those orbitals, whether it is unpaired or it paired, or the 3d orbital, it may be vacant. Depending upon unpaired electrons, we can determine the color of that elements. Then when beam of light falls on the element, it absorbs the particular wavelength light energy from that beam of light from electromagnetic radiations, and that energy absorbed by the electron, that is unpaired electron present in the orbital, and it promotes to the higher energy level. But when it is in isolated form or in atomic form, that d orbital is degenerated orbital. Degenerated means which having same energy. Here now it is degenerated orbital. 3d orbital is degenerated. When beam of light falls on it and energy of particular wavelength radiation falls on it, then this d orbitals get they loses their degeneracy. That means they get splitted. they splitted into two sets, that is 3 and 2, and these orbitals are known as T2G and these orbitals are known as EG. That means here d orbitals, n-1d orbitals loses their degeneracy. Here they are degenerated, having the same energy, and the electrons present in it, they having the same energy, but when they loses their energy, then electron from lower energy level, it jumps to the higher energy level, and when it jumps to the higher energy level, the energy absorbed, energy of the particular wavelength absorbed by that electron, and the amount of energy of particular wavelength from visible range absorbed by the electron, then the remaining energy or of particular wavelength, it is emitted from the element, or it is emitted from that d orbitals. Then color of the compound of the or element is depends upon the complementary color of light absorbed by it. The complementary color of the light absorbed by it means, suppose here if red light is absorbed, red light means the wavelength of red light is absorbed by the electron present in n-1d orbital, then its complementary color is blue. That means it emits the wavelength of light having blue color. Therefore these elements shows blue color. The ions or element which contains number of unpaired electrons, then compounds are color. If unpaired electron is 0, then compounds or transition elements are colorless. For example, copper, that is copper which having atomic number 29 and it has electronic configuration argon, 4s1 3d10. In 3d orbital, all orbitals are paired. That means there is no unpaired electron present in Cu atom, but in Cu2 plus Cu plus 1 ion, when it loses one electron and electronic configuration becomes 4s0. Now 4s orbital is vacant and 3d orbital which contains 10 electrons, that means all electrons in these orbitals are paired. Therefore there is no unpaired electron in 4s or 3d. Therefore Cu plus 1 ion is colorless. Similarly, titanium 4 plus which does not contains unpaired electrons in it. That means here we can determine the color of transition elements depending upon number of unpaired electrons present in the n-1d orbital. Then there are few more reasons of the color of the transition metals. Then we will discuss about that. First, see here, one reason for color of the transition element is presence of unpaired electron, present in n-1d orbitals. That is the one of the reason we have discussed detail about that. Then second one reason is that DD transition. Transition means promotion of electron from lower energy level to higher energy level. I have already explained about that. When beam of light falls on the d orbital of transition elements, then degeneracy of these d orbital is loosened by it and it gets split into two sets of energy levels, and electron which is lower energy level from d orbitals, it is also of d orbitals, it jumps to the higher energy of d orbital, and that is the DD transition. The energy required for that promotion of that transition of electron from lower energy to higher energy, that the color of that compound is depends upon that amount of energy. Then color of the element of transition element and their compounds is also depends upon DD transition. Then one more reason is there, nature of ligands. Nature of ligands. Ligands, that means in complexes central metal ions are surrounded by a group of particular group of the element or ions. These are called as ligands. For example, when that is nature of ligands, color of the transition element is depends on it. And one more reason, that is geometry. That is geometry. All of you studied about that. Geometry of the complex or compound. Geometry of the complex and compounds. These 2 points I have discussed before. Then we will discuss about the color of the compound, how it is depends upon nature of ligands and geometry of the complex. Then we will explain one example. Taking one example, suppose cobalt chloride, that is cobalt chloride, which is when it is dissolved in water, then it forms the complex like Cu2 plus ion, and that Cu2 plus ions are surrounded by 6 water molecules, and 6 water molecules is nothing but it is ligands. That means Cu2 plus ions in aqueous medium. Suppose here Cu2 plus ion is there and it is surrounded by H2O, 6 water molecules, isn't it? Then here H2O is ligand. There is 6 water molecules which is surrounded to the CO2 plus ion. Then see here it is in octahedral form. That means geometry of this complex, that is when copper chloride dissolved in aqueous medium, then CO2 plus ions are surrounded by 6 water molecules. Then geometry of this compound is octahedral. All of you aware of that octahedral property of octahedral geometry of compound. Then the color of that compound is, it is pink in color, but when HCl is added into it, then this complex is converted into CO2 plus ion is now surrounded by Cl minus ions, and there are 4 Cl minus ions surrounds to the CO2 plus ions, and which having tetrahedral geometry. Therefore here the geometry changes, the nature of ligand changes, therefore color of that solution also changes. Means when hydrochloric acid is added into the aqueous solution of copper chloride, aqueous solution of copper chloride is originally pink in color, but when hydrochloric acid is added into it, then it turns to blue color, and that color change here is depends upon geometry of the compound or complex and nature of ligand also. That is about the color of the transition elements. Then we will discuss the next property, that is catalytic property of the transition element, in next lecture.